Now let's talk about the electric potential due to a point charge. So again, if we define V equals 0 at R equals infinity, we want to find the potential at a distance r away, right there, from a point charge plus q. So here we are at plus q, r away from it. So you can just ask, like, how much work would it take us to bring in a 1 coulomb charge to there? Or you could say, how much negative work would the field do as we bring a plus q charge of 1 coulomb into there? Mathematically, we're going to do this with calculus. You can just ignore this if you are not using calculus, but here's the fundamental way we have to define this. The delta V is the opposite of field dotted on dr, just like the delta U would be the opposite of the work done. Delta V is the opposite of the work done per unit charge. And the field is the force per unit charge. So it's basically the negative integral of E dot dr as we bring in the charge from r equals infinity to r equals r away right there. And then when you do the integration, this is the field strength due to charge positive q. This is the field due to positive q, kq over r squared. When you integrate that with respect to r, dotted on dr, you get negative of negative kq over r. And again, we integrate it from r equals infinity to r equals r. And here's the bottom line that everyone has to have. The potential due to a point charge q at a distance r away from the point charge is kq over r. Of course, this only works if we define V equals 0 at r equals infinity. So this is now the electric potential at r away from a charge q. Now, if we change positive q to negative q, what happens to the potential? It becomes negative. So in other words, kq over r still works. And that just means that you would have to do negative work to bring in a positive test charge from infinity. In other words, the field would pull this in. Let's go ahead and look at our example. If you are bringing this charge in and this were a negative charge, you would have to pull against the force. You'd have to, oh, this is pulling me in, I gotta stop it. So to be at rest, you would have to do negative work. The field, although, as it goes from here, does positive work, because both the force is in this direction and the displacement in same direction, the field does positive work. So that means because it's the negative of the work done by the field, it would be a negative change of potential. So it's downhill from infinity, downhill from 0, means it's got to have a negative potential at that point right there. Okay, let's go ahead and do this example right here. When you're calculating work required to bring a charge Q1 in from infinity, and it starts at rest, and you want to bring it into with a distance r of Q2, which Q goes in the equation for V? In other words, I want to bring in a charge Q1 to within r of Q2. Which one is creating the potential? It is the one that creates the potential. The one that remains still is the one we will go in this equation, V equals kq over r. Q2 is creating the potential. Q1 is affected by it. So this is the potential created by Q in this equation right here. Show that conservation equation that could be used to determine the work required by you to make such a move. Well, again, we start with the conservation of energy master equation. The initial energy is U initial. The work, you will have to do some work in this situation. That's work non-conservative. And that will equal U final because we're going to move it, but that's going to remain at rest still. So there's no kinetic energy. U initial is Q1 times V initial. But notice that V initial is caused by Q2. Plus whatever work we have to do is going to be the final potential energy of Q1, which is going to be Q1 times the potential caused by Q2. So that's going to give us Q1. We are saying that we started at infinity. V initial is 0. That's going to be 0. Work non-conservative, so we're trying to figure out the work caused that we have to do. And that will be Q1 times the V caused. Here's the V caused by Q2. KQ2 over R. And when we finally solve this, we get the work that you have to do is K times Q1 times Q2 over R. That is the work done by you to move Q1 from infinity to within R of Q2. Always start out with this. If it ever asks how much energy or how much work is required, start off with your conservation of energy equation. How about this? What's the charge on a Van de Graaff generator of radius 0.1 meters if V is 900,000 volts at its surface? Now, what do we mean by 900,000 volts at its surface? That's got to be compared to something. So obviously it's compared to infinitely far away, or simply the Earth, because the Earth can be considered to be where charges can get infinitely far away. So 900,000 volts compared to infinitely far away, which is really the same thing as saying compared to the Earth, where charges can move as far away as they want. So what's the charge on that Van de Graaff generator? Hint, it's 0.1 meters in radius. It's a sphere 0.1 meters in radius. So all we got to do is, spherical charge is just like a point charge. So the potential caused by the Van de Graaff generator is K times the Q on the Van de Graaff generator divided by R, where all the charges are. So what we have here is a Van de Graaff generator, and it's got all these positive charges on the outside of it because all the charges on a conductor will spread out. So this is 0.1 meters. And so this is V at this point right there. V equals 900,000 volts. So it's just as if all the charge was right there, because a spherically symmetric charge is just like a point charge, and it's just the same thing. What's the potential out there if all this charge is right there? The potential caused by this Q, as if it were right there, V caused by Q, is equal to K Q over R. And it's the same thing. If this is all spread out evenly, it's just as if that charge was at the center. Solving for Q, you get V R over K equals Q. Doing the math, you see that it's 10 microcoulombs on that Van de Graaff generator. What is the potential at the center of the Van de Graaff? So if it's 900,000 volts at the surface, what is the potential right here, literally at the center? Hint, what is the field in here? What's the field inside this conductor? It could be hollow or it could be solid. It doesn't matter because all the charges on the outside, the E is equal to 0. How much more work would it take to bring in a charge? Here's a little Q naught right out here. How much more work would it take to bring this from there? Okay, so infinity to there, the difference is 900,000 volts. If it were 1 coulomb, it would take 900,000 joules for us to bring it in. How much more energy would it take us to bring it in to the center? If the field is 0 in here, it would take us no more work. In other words, we get a free ride. What's the potential at its center? It's still 900,000 volts. E is equal to 0 inside, so no additional work can be done by the E field. Once you get to the surface of a conductor,
in electrostatic equilibrium,
V is constant as you go further inside, as long as there's no charge in the hollow part. If it's a solid conductor, the potential is constant. Let's call that R equals 0 right there, and we'll call the radius of this thing R. Here's what the potential graph looks like. Here is V versus R, and it starts off way at R equals infinity. What's the potential? Well, it's 0 there, but we'll never get to there. We're going to start off here where it's very low. And the potential goes up as you get closer. At distance R right there, the potential, this point right there, V equals KQ over R. Right there. What is it as you get farther in? It stays the same. Notice it doesn't go to 0. It just stays at whatever level. This is a 1 over R relationship. Notice that inside V is a constant. inside. As long as there's no charge inside, it's a free ride. Once you get your test charge to this point, you can just have a ball, you can just move it all around in there, and it takes no work to do that. The potential is constant inside. And once you get, if this were a solid conductor, it would also be true because the field is zero inside a solid conductor. Volt you overcharge, volt you overcharge. I'd love to be so carbon free, but my wallet ain't that large. Unless I win the lottery, you won't be seeing my garage. Volt you overcharge.